Good morning. hello. Okay. Hello, 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 check, hello.
The sky is not the limit, it's just the beginning. Good morning to one and all. I am delighted to extend a warm welcome to all the dignitaries on the dais, heads of various groups, sections, and divisions, and all my esteemed colleagues who have joined us either in person or online for the first National Space Day celebrations at CDAC Thiruvananthapuram. Today marks a significant milestone as India is celebrating its maiden National Space Day with the theme Touching Lives While Touching the Moon, India's Space Saga. This day offers a moment to reflect on and honor India's extraordinary achievements in space exploration, highlighting the profound impact of these endeavors on society. The theme, Touching Lives While Touching the Moon, India's Space Saga emphasizes India's commitment to exploring space while making a real difference to society. A highlight of this celebration is Chandrayaan 3, which achieved a historic milestone with its soft landing near the lunar south pole on August 23, 2023, making India the fourth nation to land on the moon and the first to reach its southern pole. This remarkable achievement, coupled with the deployment of the Pragyan rover to explore the lunar surface, underscores India's technological excellence and holds the promise of benefiting humanity in future. To commemorate this landmark event, the National Space Day will be celebrated annually on August 23rd. CDAC Thiruvananthapuram has had a very close association with the space sector in India for the past 15 years. Our notable contributions to the Indian space program include ultrasonic solid propellant burn rate measurement system and the sonic ultrasonic non-destructive test system developed in collaboration with ISRO. These systems were employed in the qualification test for the prestigious Chandrayaan 3 and Aditya L1 missions. In addition, the precision instrumentation amplifier developed by CDAC was unveiled by the ISRO chairman at Satish Dhawan Space Center, Sriharikota in the context of the Aditya L1 mission last year. We are incredibly proud of our role in supporting these missions and our contribution to India's achievements in space. Our continued involvement in such groundbreaking projects reinforces our commitment to advancing space technology and exploration. The first National Space Day celebrations at CDAC features an invited talk by Sri Pradeep Kumar P, Deputy Head of Atmospheric and Space Science Avionics and Checkout Division, Digital Systems Group at Vikram Sarabhai Space Center, Thiruvananthapuram. He is joined on the days by Sri Rajesh KR, Scientist G and Group Head, Strategic Electronics Group, CDAC Thiruvananthapuram. I invite Sri Rajesh KR for the welcome speech. Welcome, sir.
Very good morning to all of you. Our chief guest Sri Pradeep Kumar P, Deputy Head ASCD Digital Systems Group Avionics Entity VSSC Thiruvananthapuram and my dear colleagues. See, as we all know and just mentioned, we have assembled today to celebrate the first National Space Day in India today. India became the fourth country to land on the moon and the first to reach its southern polar region on last year, August 23. To honor this landmark achievement, our Honorable Prime Minister Sri Narendra Modi ji announced August 23 as National Space Day. India is celebrating its maiden National Space Day today with the theme Touching Lives while Touching the Moon, India's Space Saga. As we all know, ISRO and its various labs and centers have been leading our country's space endeavors since its formation. CDAC is very proud to have had a long-standing relation with ISRO for the last 20 years in developing indigenous products and solutions for the qualification test of various mission critical applications. We are pleased to share that some of these products have been extensively used in the prestigious missions such as Chandrayaan 3 and Aditya L1, and it will be used in the incoming missions like Gaganyaan, etc. These are all various mission critical applications. We are pleased to share that some of these products and its details. The first one is ultrasonic solid propellant burn rate measurement system. It is actually developed jointly with VSSC. Actually, the requirement came from the VSSC. We studied it extensively and we developed a prototype model, and it has been tested rigorously at VSSC, and then we started getting order for that. And this system is used for the precise measurement or the accurate measurement of the burning rate of solid propellant. Solid propellant is the fuel used in the booster stage of rocket. So this is now a mandatory test for qualification of solid propellants. Now we have extended this product, and we are offering this to various missile labs of DRDO, because the missiles also using solid propellant. Only difference is that the burning rate is much higher, about 4 to 5 times than the solid propellant used in ISRO rockets. It is 5 mm per second is the normal burning rate. 5 millimeter per second is the burning rate normally used in ISRO rockets, while missile labs use around 30 millimeter per second, because it has to reach the target at the shortest time. Then the second our product is sonic ultrasonic non-destructive test system sound system. This system is used for thickness measurement of the booster stage rocket insulation layer propellant inhibition layer, and a bonding integrity testing of acoustic sound form used in the orbiter and lander modules, that is the payload modules. It is also employed for flow detection of various components used in the cryogenic unit and payload adapter unit. Actually, these when we delivered sounds for the first time, we didn't envisage such application. But ISRO took it our product into a higher level, where they have mastered testing our equipment for the various purposes like I mentioned. Then the next one is a product. Actually, in CDAC Trivandrum Center, we have 9 technical groups. So the next product, integrated telemetry test station, is developed by combined development of 3 groups: control and instrumentation group. Jerry is here heading the group, and strategic electronics group, and hardware design group headed by Krishna Kumar Rao. So this station is designed for testing the telemetry packages of the launch vehicles developed by VSSC. It caters to the testing needs of advanced telemetry system stacks used in different ISRO launch vehicles such as PSLV, GSLV, LVM-3 and ATV. Recently we have developed one more product, that is a high precision instrumentation amplifier. As I mentioned, all these requirements came from the ISRO or SHAR center, because they have satisfied with the products that we delivered. So this product, precision amplifier in preamp in short, launched by the chairman of ISRO Somnath sir at Satish Dhawan Space Center, Sriharikota, on last September 1, 2023, along with our Director General Magesh sir. This prestigious event was in the backdrop of Aditya L1 launch. This is a high accuracy instrumentation amplifier used for measuring critical parameters during the static firing test of rockets. We received a letter of appreciation from the director of Satish Dhawan Space Center, SHAR, as well. We also had a rare opportunity to witness the launch of Aditya L1. That is on a special invitation we received from the ISRO. That was one of a rare event in our career. So when the rocket launches from the pad, and that visuals will give goosebumps actually. That is something, a very rare opportunity that we get. We really cherish that in our moment, in our life or in our career. Now moving on to the duty vested upon me, it is my privilege to welcome our Chief Guest Sri Pradeep Kumar P, Deputy Head ASCD Digital Systems Group, Avionics Entity VSSC Thiruvananthapuram, who has 35 years of experience in the design and development of data acquisition and control system for the ground-based experiment systems, as well as the scientific payloads for planetary missions, which are many of our very critical planetary missions. And sir was telling that sir was preparing the presentation till yesterday morning 4:30 a.m. and we are very eagerly waiting for his talk on the topic challenges in the development of electronic packages for space applications and general failures. Sir was telling this was basically aimed for our young engineers. Sir expect questions means from you during the presentation itself. Maybe sir will be telling that. So you can use this opportunity to see that how ISRO achieved this success, how the electronic packages ensured that the success happened, and still there are failures, how they overcome these failures. Sir was telling it will take hours to share all his experience, but I said, sir, we will have enough time till 1 hour. So on behalf of CDAC, sir, I extend a very warm welcome to you to this function. Now I welcome all the group heads, section heads, and one and all present in this hall to make this function a great success. Thank you all.
Thank you, sir. Sri Pradeep Kumar P is a distinguished scientist with over 35 years of experience in the design and development of data acquisition and control systems for ground-based experiment systems and scientific payloads for planetary missions. He is currently serving as the deputy head of the Atmospheric and Space Science Avionics and Checkout Division of the Digital Systems Group Avionics entity at Vikram Sarabhai Space Center, Thiruvananthapuram. Sri Pradeep Kumar P holds an M.Tech in Applied Electronics and Instrumentation, B.Tech in Electronics and Communication Engineering, and Diploma in Electronics Engineering. His vast experience and expertise have been instrumental in some of India's most significant space missions. He has played a pivotal role in several landmark projects, including the Chandra's Altitudinal Composition Explorer, CHASE, onboard Chandrayaan 1, where he contributed immensely to its design and development. This instrument achieved a groundbreaking discovery by providing direct evidence of water in the lunar atmosphere. He also designed and developed the onboard system of the MENSA payload for the Mars orbiter mission Mangalyaan, which provided valuable insights into the Martian atmosphere. For Chandrayaan 2, he was responsible for designing and implementing the onboard system for the Chase 2 payload, continuing the work of its predecessor in studying the lunar atmosphere. His contributions to the Rampha LP payload on the Chandrayaan 2 lander and Rampha LP-2 on the Chandrayaan 3 lander further showcase his expertise in creating systems essential for the operation and control of these missions from the ground. In addition, he is currently involved in developing scientific payloads for several upcoming missions, including the PS-4 platform payloads, Venus, MOM-2 and Disha. He also holds a patent for the solar radiometer, a scientific instrument designed to automatically track the sun and measure its multispectral intensity, which is crucial for studying atmospheric aerosols. Given his extensive contributions and profound impact on India's space exploration efforts, it is an honor to have you, sir, in our midst today. I now invite Sri Pradeep Kumar P to deliver the invited talk. Welcome, sir.
Good morning. I am very happy to be present here, and I was listening to Rajesh sir's presentation. Then only I understood that you people are doing the same level of work what we are doing there. And I had a discussion also earlier. So I understand that you are doing applications for missile as well as launch vehicles also, and satellites too. So that means the level of expertise you are having is almost same as what we are having there. So the topic given to me was actually the challenges and in failure analysis as well as failure detection. So this is a new topic for me, even though we are working in that area. Topic wise it is new, and I never had any presentation before that on that topic. So day before yesterday only this was finalized. Yesterday night only I could prepare some slides. So till 4:30 a.m. I was preparing that, and hardly I could sleep for 2 hours. But this thing is that I have made lot of material thinking that because you people wanted more technical content in that. But after coming here, I understood that you are more interested in knowing our practical experience in ISRO. So there is a dilemma now. Okay, so what I will do is I will go through those presentations, and I want you to interrupt me and ask questions so that it will be more interactive rather than monotonic presentation by me. But you can go through the slides, whatever points I have listed there, because these points are from the my own experience. So they are relevant also. But if I start explaining each and every point, it will take more time. So whichever interests you, you can ask me questions. So that is the way I wanted to proceed further. Okay. So the presentation, it is like this. Actually, it is organized like this. Can I slide? Next. Yeah, this is the outline of my presentation. So I'll be covering the challenges in space realization of electronic packages. So what are the challenges when we are realizing electronics packages for space applications? Then areas of challenges in realizing a scientific payload. This is as a case study, because I have more expertise in developing scientific payloads right from Chandrayaan 1. I have been working on that, so almost 2 decades of experience is there. So as a case study, I will be presenting scientific payload development and the challenges faced in that. Then in that I will be covering the various platforms of scientific measurements, then types of measurement, then requirements for design and realization, then testing and qualification. These are covered under that case study. Then coming to the topic which you wanted me to talk, that is the general failures and failure analysis. So these only the new slides I have made actually. All slides are previous slides which I already had. Then fourth one, if I get time, that is the most interesting topic for me actually. Wherever I go, I will talk something about ISRO actually. So fourth one is the major milestones ISRO has covered so far. If I get time, I will cover that. Otherwise, already you all know that, but I will be able to tell something which you are not come across in the news or media. Next slide. Yeah. Okay, next. So various challenges in space, it is summarized here actually. So one of the main challenge in space is very high temperature and very low temperature, the most challenging. Then high energy radiations, high energy particles. Then vacuum, high level of vacuum. Then space debris, okay, micrometeorites. So these are the major challenges we face. Then very high magnetic field also. So to list those things, we have vacuum, zero gravity, then hazardous radiation, very high and very low temperature, meteorites, micrometeorites, cosmic clouds and dust, then heavy shock. So you will think where this heavy shock is coming in space actually. This is coming out of the, when the satellite is separating from the launch vehicle, there is a heavy shock. And when the satellite is also, when there is something called momentum dumping actually. So during that also shock will come. And if any motorized thing is there, that time also shock can come. So this is the shock we are talking about. Then severe vibration. That also, when launch vehicle is going up, there will be heavy vibration because of the engine performance. Then there is a motorized operation also will create vibrations. Then extreme acceleration. Launch vehicle also is accelerating very high acceleration. Then low power. This is a challenge actually, because in a space system, any rocket, if you consider the weight of the satellite, the purpose of the rocket is to take the satellite into the space actually, but the weight of the satellite is only 0.5% of the total weight. If this launch vehicle is 100 kg, only 500 gram is the satellite. So that is the ratio, almost 200 times is the weight of the rocket itself. So if you want to fly anything in space, the weight should be very less, because 200 times you have to add the weight for the launch vehicle actually. And most 90% of the weight of the launch vehicle is the fuel itself. Then power also, because in space you cannot generate power, you have to depend on the solar power, because battery you cannot carry. So solar power you have to depend, so power also should be very minimum. Then volume, and then the outgassing. That is actually, if you are carrying anything into space, any material will outgas actually. Solid form to gaseous form it will come. So this outgassing in space, there is no atmosphere. So whatever gas is coming out of this, whatever material you are carrying to space, that will form a cloud around this satellite. So that can create problem to the mostly the optical components. Like if you are having a camera or anything, it can form lot of issues, like fog and all will come. So outgassing should be the minimum. So whatever material you select for space application, it should have very low outgassing. Then these are the challenges in space for humans actually. Whatever general challenges, some of the challenges are for the humans also. So like space radiation and charge particle can create problem. Then vacuum is a problem. Then isolation from confinement means in space means they are isolated from the ground and their family. So that is another problem. Then distance from Earth. If we are going abroad, some kind of fear we all have actually. The far we go from our house, the more we get fear actually. So if you are going far away from Earth, fear will be more actually. So that is another problem. Then gravity fields, then hostile closed environment, because he has to be protected from the hostile environment. So he will be in a very closed protected environment. So that claustrophobia also will come. Then lack of oxygen and pressure, because normal pressure is not there, it's high vacuum. Then micrometeorites, any micrometeorites can create problem. It can puncture the launch vehicle or the satellite or the crew module. Then other effects for space flight. So these are the challenges a human will face in space actually. So the various challenges human will face in space, one of the main challenges is the gravitation, microgravity. So these are the issues we face in microgravity actually. Weightlessness is a problem, because we will be always floating. Then drinking, you cannot drink water, because water will not come. And we are easily drinking because of the gravity only. So he has to sip up water. Then bathing issues, he cannot bathe. Then sleeping issues, because if we sleep in one place, you will be waking up from another place, because he will be floating. So those issues are there. Then combing issues, hair will not stay. So there are so many issues, you can read that. I am not dwelling all those things actually. There are so many issues in space a human is facing actually. Yeah, damage to brain is actually, in microgravity, all the body fluids will go to the brain actually, because due to gravity only they are coming down actually. So heart will be pumping, so all the body fluid will try to go to the brain actually. So it will damage the brain also. Prolonged stay in space, muscle damage is one of the main damage, then brain also, and psychological damage also is there actually. So these are the hostile environment of the space. This also you are very much aware. I am not dwelling about these things. To summarize the challenges, shock, acceleration and vibration in launch vehicles. So we will be facing 10 to 24 G RMS, and shock also some 600 G. So these are the uh, any electronic package you develop, it has to undergo all these challenges actually. Then 600 G is the normal shock actually. Now we are testing one of our package for the next PSLE mission. We are told that 1500 G is the shock. So now we have to test for 1500 G, all our packages. And it has survived that shock also. Then extreme heat, so minus 155 to plus 150, that much heat will be there. And in moon actually day and night variation is almost this much. And extreme vacuum, then extreme radiation, then deep space communication. Because in deep space communication, some Mars mission, if you remember, it was going away almost some 40-50 crore kilometer away from Earth actually. So that much distance we have to communicate without any issue actually. So communication itself will take some 20 minutes to reach to and fro time. It will be almost 20 minutes during Mars mission time. So any command given there, you will know only after 20 minutes that whether command has been reached there or it has been executed also. Then as I already told, this power generation and support during the mission. And eclipse also, during the eclipse, solar panels will not generate power. So you have to take care of the eclipse. So that much battery you have to carry considering the eclipse. So all these calculations you have to do prior to the mission itself. Then weight and outcasting I already told you. Oh, I didn't. Okay. So how to overcome all these challenges? What are the methods? So the methods are actually identifying proper components and materials. So that material or component which you are going to select should withstand all this hostile environment. That is the prime thing actually. So first and foremost point is identifying the components and material. Then some components, because normally we go for mill grade or space grade for applications. But some components will not be available in mill or space grade. But it is available in industrial grade or commercial off the shelf grade. So that components, if you want to use, you have to use quartz components, but you have to upgrade that component by screening or some ruggedization methods, because you don't have an equivalent space or mill qualified component. So that is one challenge, qualifying the quartz component. Then procurement and screening. You have to procure the component from a known source or reliable source. Then once you get the component, you have to do screening for the performance of the component. And when you are sending a payload in space, you may not be able to communicate all the time with the payload actually, because it may go other side of the Earth, then you don't have any communication. And if you are going to moon or Mars, it may go other side of the moon or Mars, then also there is no communication. And for the Aditya L1 case, there is nothing in between Aditya L1 and Earth actually. So there is always line of sight is there. But the problem is Aditya L1 is put in a point called L1 point, the Lagrangian point. It is a point in the straight line between Earth and the Sun actually. So if you put a satellite there, if you want to communicate with that satellite, your antenna will be always seeing the intense radiation from the Sun. You cannot see the mild radiation coming from the satellite. So you cannot communicate with the satellite if satellite is put in L1 point, even though there is no obstruction between the line of sight. So what we have done is we have put the satellite in a halo orbit around the L1 point. So satellite will be orbiting around the L1 point. So whenever you look to the satellite, you will be slightly some 4 or 5 degree away from the sun actually. So you won't see the sun radiation, you will be seeing the radiation coming from the satellite. So these are the challenges when we are communicating with the payload. So payload should have autonomy. That means if you are not able to communicate the payload, payload should be able to take decisions based on the current outcome. So that is the payload strategy. Then approved fabrication procedures. Whatever fabrication you are doing, you have to go through the approved procedures only, no deviation in that procedure. Then qualifying for vibration, shock, temperature, vacuum levels. So we call it actually test and evaluation actually in short. So in test and evaluation, we have to do all these tests. So there are 3 levels of test. One is the designer level test. That is basically for the functionality test actually. We want to know whatever we make, whether it is meeting the required functionality. That is the designer level test. Then comes the qualification level test. That is for knowing the margin, how much margin you have put in the design actually. Suppose your design is supposed to work for 100 degrees centigrade. If you are designing only to meet 100 degrees centigrade, if it goes to 101 degree, it may fail. So we should have a margin actually. So normally the margin we are giving is 1.5 times. If it is supposed to work for 100 degree, it has to undergo up to 150 degree temperature. In 150 degree also it should work fine. So this is the qualification test. So that is to get the margin, how much margin you are given in the design. So all the design margin will come out in the qualification test. Then the third test is the flight acceptance level test, actually FAT we call it. So in that, that is the final test done before integrating this package with the launch vehicle or the satellite. So in that test, what we are doing is we are just testing the functionality and also testing whether any workmanship errors are there, like soldering errors or assembly errors. Those things only will be testing. So that will come out in vibration, in thermo vacuum and functional testing actually. But we will not subject to 150 degree. If you subject to 150 degree, what will happen? We are overstressed actually. So there is a chances of failure is very high. So whatever package we do qualification test, we will not fly it. Okay, we will fly whatever package we make in FAT only. So normally the design philosophy will be going for 3 model philosophy, one engineering model that is for functional test, design analytical test, and this qualification model that is for knowing the margin, then flight model that is for finally flying. So all these tests, qualifying tests will be done on the QO model, then testing for wide temperature range, so minus 55 plus 125, then radiation testing and qualification, and overcoming communication issues, visibility of that already I mentioned, then meeting stringent fabrication and handling, because fabrication is one thing, then once you get the item in your hand, you should properly handle it also, because some of the things, even fingerprint can cause problem actually. I made one package for the Chamba LP payload for the this lander Chandrayaan 2 and Chandrayaan 3 lander, where I am measuring actually 25 picoampere. So if I just walk around that package, I will get measurement. If I just wave my hand in air, I will get measurement. So that much sensitivity. So if I put my finger on the circuit board, it will saturate. I will not be able to make any measurement. So handling is very critical actually. So we should handle properly. Then another thing is the ESD actually. So human body can create a lot of ESD shock to the component. So ESD failures also will come. It may not be appearing when you are testing actually. It may appear in space sometimes. So handling is very critical. Ah. Yeah. Yes, yes. Yeah, actually during the launch we have what is that interaction with other countries like NASA, ESA and JAXA also. So we will use their earth stations and they will be receiving the signal and they will communicate to us. That is what we are doing actually. So there is a collaboration actually. And same way when they launch, we also will give support. So that is required. Otherwise, when it goes other side of the, not only other side actually, all these radars will have range some 2000 kilometers only. If it goes beyond that, then it is very difficult. So India is having one in Shar, in Trivandrum also is there. Then we have in Port Blair, and we have also kept one in Biak actually. Then we have ship-based stations also. Apart from that, we will be getting Canberra stations from USA and NASA, and some and Goldstone also is there in Africa, I think. So many stations are there. So across the globe, we will be utilizing their features. And during Chandrayaan 1 and Chandrayaan 2 time, we are having some 32-meter antenna that is sufficient to communicate with the spacecraft. But we also use NASA's 64-meter antenna because that is having more signal to noise ratio. Then another thing is that generation of extensive documentation, because any product there is a life cycle document. So like initial design document, then the review documents, then critical design documents, then software design documents. So for software also there are many documents like a functional requirement, functional design document, then functional requirement document, then software requirement document, then software design document, then impact analysis. So many documents are there. All these life cycle documents we have to generate. Some we have to generate before we start the fabrication. Some we have to generate after testing and realization of the package. So all these documents are important because most of the functions are human independent actually. Suppose if one person is working, if he is not available, somebody should be able to take care of that. That is why documentation is very important actually. And many of the failures we come across will repeat after several years also. So if it is well documented, then it is very easy to find the fault. My slide is not moving. Okay. So various areas of challenges. So this is a case study actually. This is with regard to the payload development, scientific payload development. So a scientific payload development, various platforms are available for scientific experiment actually. So low and high altitude balloons. Low altitude balloons are used for 2 to 5 kilometers. Then high altitude balloons 20 to 40 kilometers normally. So helicopters are used for up to some 5 kilometers. Then sounding rockets, we want to go up to 150 kilometers, you have to use sounding rockets. Then parachutes are used when sounding rockets going up. Now it is going very fast, almost 1 to 5 kilometers per second fast it goes. But many of the sensors will not sense that speed. So if you want to make measurements from a very high altitude, what we do is we send the payload in sounding rockets, then we drop in parachutes. So that it will come down very slowly, then we can make measurements. So parachutes are another platform. Then satellite launch vehicles. Launch vehicles also we keep scientific instruments. When it is going up, we can make measurements. Then satellite itself we can use as a platform for making scientific payloads measurement. Then drones. So measurements, these are some classification I have made myself. I do not know whether it is really that way. But from my experience, I classified this like this: in situ measurement and remote measurement. In situ means if you want to make a measurement at some place like a 2 kilometer height, what is the wind, if you want to know, you have to go to 2 kilometer and make measurement there actually. That is in situ measurement. Then remote measurement means you can measure from ground itself what is the wind velocity at 2 kilometer. Okay, sorry. Then active probing and passive probing. Active means like a laser and all you can probe using active probing. Passive means if you are making the solar radiation measurement, it's a passive measurement. You are not probing anything, you are just getting the radiation or measurement. Then direct measurement and indirect measurement. Direct measurement is like a thermometer is measuring the direct measurement, it is measuring the temperature. Indirect means like surveying you have seen, what seal people are doing on road and all, they are using theodolite for surveying. They are measuring the depth of the soil or the height of the soil by indirect measurement actually. By triangulation only they are doing. That is indirect measurement. They are not really measuring with a scale what is the depth or height. So requirements and design of a scientific payload. So this is the starting point actually. If you want to make any system, you should first know the requirements first. So first you categorize the requirement, and based on the requirement you should start your design. So to summarize that, measurement parameters. So that is the first point actually. What are the parameters we are going to measure and their range. Okay. Then sensors and their selection. So if you know what are the parameters you want to measure, you have to choose a sensor suitable for measuring that parameter, and that sensor should have the correct range also, and the error also of the sensor should meet your requirement. Then front-end electronics. So sensor has to be interfaced with some electronics. Some sensors require some excitation, some sensors do not require that. So your front-end electronics should cater to interfacing the sensor to the rest of the system. Then control and data action. Any measurement needs some control actually. Either suppose if it is an active sensor, if you have to give excitation, you can control the excitation. Okay, whether it is 5 volt. So in the case of this Ramba payload in Chandrayaan 2 and 3 lander, there is a probe which is measuring the radiation of the lunar atmosphere just above the ground, just 1 meter above the ground. So it is measuring the electron density, electron temperature, then ion density also. So there is a spherical probe. So what we are doing is we are biasing that probe minus 12 to plus 12, any voltage we can fix and give to the probe. So that is called control actually. So then another thing is the autonomy, which already I mentioned. Then data volume and data rate. You should know how much data volume this sensor is generating and at what rate this data is generated. So your system should be capable of acquiring at that rate as well as storing that much volume of data. Then data processing and formatting. So in space, suppose your sensor is generating lot of data, you cannot send all those data to the ground actually, because communication is a premium commodity. So you will not get that much data rate and data bandwidth. So what you have to do is you have to process the data on board itself. Only the required data should be sent to the ground. That is called onboard data processing. Then formatting the data, because any data if you send to the ground, you should know where data is acquired or what it belongs to. So you have to format it properly. So if you are having several sensors, you should have a tag for each data you are sending. So that is what we are doing by formatting. Then data storage and transfer. onboard storage should be there, then there should be a mechanism for transferring data to the spacecraft, because your scientific instrument is collecting data, transferring the data to the spacecraft system. Then payload health monitoring. Any instrument if you make, you should know the health actually. What is the temperature of the system, and what is the current drawn by the system, what is the voltage of some output. All these things we have to monitor. That is called health monitoring. Health monitoring will be, we are getting that health monitoring parameter every 2 seconds or 32 seconds. So you will know continuously on a continuous basis what is the health of the. So only selected parameters will be considered as health parameters, because that also is a premium thing. So only so in the case of Mars mission, I got only one parameter, that is 5-volt monitoring only. I wanted to monitor the temperature, I want to monitor the current of the package. Everything was available, but they gave me only one line so that I can monitor only a package on or off. Because that much only they can provide. There are so many things they have to monitor. So I have provided so many output, but I got only one. So these are health monitoring parameters. Then telemetry system. Telemetry system is whatever health parameters you are monitoring, that has to be telemetred to the ground immediately every 2 seconds or 32 seconds. Then telecommand system. If you want to control your package from ground, you should have a telecommand system so that you can give a command from ground to the package, and package will take that command and work accordingly. Telecommands are also, there are different types of telecommands. So that's something called pulse telecommands and level telecommands and data telecommands. So data telecommands means we can give any kind of data, so that various functions we can establish using data telecommands. And data telecommands also, there are two types. One is you give the telecommand, immediately that command will get executed. There is something called time tagged command also. In that you want to operate the, you are giving the command in the morning time, you want to operation only in the night, a specified time. So that time there is no visibility, you cannot upload your command. So you upload the command when there is visibility. When there is no visibility, that is the time you want to operate that command. So you time tag it so that it will get operated at the exact time when you wanted to operate it. Then power system, it has generate power from the solar panel and battery has to be there. Then mechanical system, there is a system required for holding all the instrument you make. So there should be a strong mechanical system which has to undergo all the shock, vibration and other things. And environmental protection also, mechanical system is required. Then operation schemes. There are general schemes and mission critical schemes, special schemes. So these are the major requirements you have to consider when you are designing a payload or any instrument for space applications. Okay. Coming to testing. So requirements is there, design is there. Now you realize the package, how to test it actually. So here I already mentioned shock, vibration. This already I covered, so I will not dwell on this. So now we'll come to general failures, the topic which you wanted me to talk. So how to detect failures and how to do failure analysis. So type of failures are there. So preventable failures. Some failures can be prevented actually. You can, if you know, you can prevent that failure actually. And some failures cannot be prevented. That is also there actually. And some can be mitigated. Mitigated means failure has happened, but still you can use that device or equipment with some limited performance or with some limited error conditions, like certain kinds of errors it will not respond. Okay, if that error is not happening, it will work perfectly fine. But in that case, it will not work. Okay, so that are called mitigatable. So mitigable errors actually. So this can be used with a limited performance. Then unavoidable errors are there. Okay. Oh, again it does not come. Sorry. Okay. Unavoidable means you cannot avoid. Natural calamities and all are there that you cannot avoid. Then due to lack of awareness also failures may happen actually. Because somebody might have done something. One of the failure happened in Shar. They were casting the motor case. Okay, so one team has done the casting and they have gone for lunch. The next team came to take up that work further actually. But the people who went for lunch did not do some safe arming. They forgot to do that. They didn't communicate to the other team that such a thing is not done. So they came back and resumed the work thinking that it is as usual everything. So explosion came and so many people died also. So similar failures can happen due to lack of awareness actually. That also can be avoided actually. Then coming to the type of failures. So generally we can say that hardware failure and software failure. So in hardware also electronic component failures are there. Then component failures also, then excess temperature failure can happen, then high current failure, high voltage failure, then due to ionization failure can happen, then due to moisture also failure can happen, then air trapping. Sometimes the components we buy, they are not hermetically sealed, so air will be entrapped inside the component. So when you do conformal coating, that air will be trapped inside. So once it go to vacuum, this whatever air inside is at atmospheric temperature and outside is vacuum actually, it will burst. So it will crack the device. So this is also a major failure for components actually. Then vibration shock related failures, then design error failures, because failures can happen because of the design errors also, and design margin errors also can happen. Then handling errors, I told already, handling can create failures. Then tinning, when you are doing the tinning of the components due to excess temperature also failure can happen. Then soldering time also failure happens. Then many other cases are there for component failures. Then PCB related failures, another failure is mostly PCB related. There also mechanical failure can happen, elastic and non-elastic or plastic failures. So elastic means it can come back, because if there is a stress on the PCB may bend. But that once the stress is relieved, it will come to normal. That is called elastic actually. But plastic means even if you release the stress, that deformation will remain there. So that kind of problem will come for PCBs. Then thermal issues, high temperature, if it is there, glass melting point, then it can melt, because PCB is made out of glass, resins and other things, copper also. Then environmental problems like foreign particles, okay, can get trapped in the PCB in the process of PCB fabrication. Then moisture and dust also can create problem. Then power surges also can create problem for the PCBs. Then temperature issues. Then electrical stress actually, that is high voltage, high current, then ESD, then surface breakdown and dielectric failure. These are the common failures we are facing in the PCB actually. Then PCB assembly and fabrication related failures are also there. That is wrong components putting, means instead of putting one op-amp, you may be putting say regulator there actually. It may be having, both may be having same size, same footprint. So the assembly person may by mistake put a wrong component there actually. Then wrong position, the place where you want to put 10K, somebody has put 1K and 1K is put in the place of 10K. That is wrong placement actually. This is another common failure we are seeing in the assembly of fabrication process. Then wrong placement, 10K is put in the place where 10K has to be put, but the orientation is slightly different. So it is not properly sitting or it is shorting the pads. So that is another issue. Then tinning and soldering related issues I already mentioned actually. Then device crack. So device crack can happen during fabrication of the device or during the process of the assembly, and peel off and other things are the normal component failures. Then white spot, due to over temperature during soldering and all, white spot will appear in the PCB. Then coating and potting actually. When you are doing conformal coating and when you are doing potting also, failures can happen to the PCB actually. So I told for the mass mission I am measuring this 25 picoampere. So now for the POEM mission in the this October we are sending, there I am measuring 10 picoampere. So I don't want to do any conformal coating in the electronics component where I am measuring this low current, because conformal coating material will form a separate path. Even though it is high impedance, that path will create a lot of leakage current for me, and which will be much more than the 10 picoampere which I am measuring actually. So I will not use any conformal coating in the area where I am putting these components. So conformal coating also can create sometimes issue, even though it is done for protecting the PCB from the environmental issues. Then potting also. When you are potting the component, potting is done to avoid any problem with vibration or shock, because component may not be having enough mechanical strength to hold by itself. So we will be giving additional strengthening for the body to hold it with the PCB. That is called potting actually. For that we will be using certain RTVs. So this rubber compound sometimes can create issue. So in my case I will not put any potting material in the devices which I am using for very low current measurement. And one problem we faced during Mars orbital mission time was I made the card, complete testing was completed, and final stage I had to do the test and evaluation. Before test and evaluation, I had to do the potting actually. So we had done one card potting and successfully we had done testing of that. So flight card I am making now, same way it has to be made. Okay, but what happened is the day when I gave the flight card, the operator got changed. Okay, the person who did the work on the flight card was not the person who did the work on the qualification model actually. But the document says everything. He has to follow the document, but even though he is following the document, he made it a different way. So I had to pot using a die-cast. Die-cast is a material for potting as well as for thermal heat sink purpose also you will get actually. It will dissipate the temperature. So I want die-cast, very solid material actually, very strong. It is like araldite actually. So I told him to pot the die-cast over the component. So there are some 3 ICs nearby. So he thought all the 3 needs die-cast. Why don't he put everything together? So he made a bridge of die-cast over 3 these ICs. Okay. After this potting is over, I just took it up, and when I gave power, it was taking very high current. I found that all these 3 devices has failed. Okay, he has not done anything. He has just potted the material over all these 3 things. So they got bridged. So during the curing process, it was shrinking. So it broke the components actually. So that is the mistake he has done actually. So had it been done individually, this would not have happened. So I had to go to ISRO headquarters and I had to explain to URO why it happened and all. So that much level it goes. Something happens to the flight model actually. It will be known to everyone in ISRO if something goes wrong with the flight model. So this is one issue with the potting. Then interconnection issues, connector issues. So when you are mating connectors, sometimes one lead may be bent, one pin may be bent. So without knowing that, you will be inserting it, you will apply a lot of force. That lead will bend and it may short with other leads. So these are some issues with the connectors actually. Then loose connection is another issue with the connectors. Then harness related issues. Sometimes you make harness, but the person assembling, because you will be using 25 pin connector, so there may be several 25 pin connectors in your package. So instead of putting C1 connector, you will put a C2 connector harness to you. Problem can happen. So what we do is maximum possible we will try to put different connectors on the package. One will be male, one will be female, one will be 25 pin, one will be 45 pin, 44 pin, like that we will put. But still you cannot avoid sometimes. Okay. Then you have to give clear demarcation of connectors. Still people will make mistake in interconnecting. So that is harness related failures. And coming to software failures, functional failures, logical failures or functional failures, then margin and limit. Sometimes if margin and limit is crossed, software can fail, which you will not know in normal operations. Software will be working perfectly fine. Like one of the failures or 2 major failures of ISRO has happened because of the software actually. Like PSLV first flight, D1 flight, it was a software failure actually. And in Chandrayaan 2 lander also, in my opinion, it was a software failure. Even though in both these missions hardware issues were there, ultimately the failure was caused by a software mistake. In D1 mission, it was an overrun actually, because they expected some sensor output to be within this range only. So the software designer considered that this is the maximum value that sensor output can go. So he gave that value only. But in mission, that sensor output went beyond the value he gave actually. Because of that, there's a sign reversal happened in the software because it is overrun now. So sign reversal happened. So the control system gave a reverse signal. So when the launch vehicle was going on, there will be deviations. So there will be small motors on the launch vehicle to correct this deviation. The main motor will be giving thrust to take it to the orbit, whereas these small rockets will be giving correction. So this correction signature means sign as reversed. So when it was deviating, the correction was further deviating it. So it went on deviating. After some point, no, this rockets is made, it can go straight way only. It cannot go like this. That much structural strength is not there actually. So beyond certain deviation, it will crash. So that is what happened in the case of PSLV. But PSLV did not crash actually. It went on deviating. All the stages performed well, including the satellite ejection, but it could not attain the orbit because of this heavy deviation actually. This is actually a software error. And Chandrayaan 2 lander also uh, up to some 5 kilometers it came down perfectly well. 5 to 2 kilometer it came down, there was an issue actually in the fine braking phase. That issue was related to the motor and other things. But what the issue was caused by the software actually, because all the engines were stopped to take the pictures. In Chandrayaan 2 lander or 3 lander also, the method is that the landing site photograph is already uploaded in the lander, and lander is also taking photograph of the landing site till it reaches the landing site, and to compare with the earlier photo and see whether any boulders or hazards are there. Any boulder which is more than 25 centimeter height, lander cannot land safely. So it should find the photograph and find out whether the boulder is more than that 25 centimeter or not. For that continuously it was taking photograph. So to take photograph, engine has to be stopped because engine is firing down. So when engine is firing, it will get only the plumes. So engine has stopped. Then it has to stabilize also to take photograph. It was taking photograph. After taking the photograph, engine has to fire again. That time, by the time, due to some error in the software, it got reversed actually. So from 5 kilometer when we restarted, it came down very drastically because the engine is firing from top. So it came down to almost some 50 meter per second velocity. It came down because we are reducing the vertical velocity. When it is coming down, it is coming some 4 to 5 kilometer per second velocity. So that we reduced by firing this engine up to some 50 meter per second. But when it got reversed, it suddenly went to 100 meter per second. Okay, not only it went to 100 meter per second, it lost a lot of altitude also. It came down from 5 to 2 kilometer very drastically. And still we have 3 more minutes of operation left for safe landing actually. We have to fire all the engines so that it can hover and softly land. But that event did not take place. Before that itself it landed. That is why it became a crash landing. So here also software only created issue. Here the software issue was that the designer thought that always that value will be positive. Okay, so he used an instruction saying that ABS, absolute value, because he thought this value will never go negative. So he used the instruction absolute value of that particular variable actually. But in the actual mission, that value went negative. Since he used absolute instruction, it gave positive output. So the control system thought that it is positive. Okay, it fired. It came down drastically. So had this software mistake was not there, Chandrayaan 2 itself would have been a success actually. So in Chandrayaan 3, all such things have been taken care. That is why we could get a good success. Not only success actually, chairman was so confident that he announced days before that it will be successful. Okay. So these are some software errors. Then error handling. In software also, you are designing it for some particular functionality, but you should also think that it can fail in several ways. So what all ways it can fail. So though all failure cases you should be able to handle. That is called error handling actually. Then overflow signer I already mentioned. Then programming and loading. You have done a perfect programming, but you have to load that program into the microcontroller or the E-square program or probe. So during loading also there can be errors actually. So that also can create software related errors. You have to alert me regarding the time actually. Okay, I am going very slow. Then types of failures, handling failures. When you handle also failures can happen. The same thing, no? Okay. Then testing failures. During testing also failures can happen. Okay. So same thing happened with me also for our Mars orbital mission. Package, final flight package was getting tested. Everything was perfectly done. But when the person was making connection with oscilloscope for monitoring this signals, a phone call came for that person. He just left the oscilloscope probes on the table and went to attend the phone call. By the time oscilloscope probe, it's a cable now, it just twisted and it just came shorted. So 5 volt and 24 volt got shorted. Immediately my card failed. Okay. So this is a failure during testing time. So what we normally do is we arrest all the cables, we put insulation tape and other thing and put tape over the probes so that no movement, even if you shake the table, no movement will happen to the connections. But This is the process of making that phone call came, interruption came, it happened. So failure can happen during testing also, and power supply settings, you have to do the proper setting for the power supplies. You have to also do the current limit for the power supplies correctly. Otherwise also these failures can happen. Then ESD, by handling, if you are not using gloves and all, ESD failures can happen. Then integration time failures. Once all the testing is over, you are going to integrate this package with a subsystem. So when you are integrating with another subsystem also, failures can happen, like wrong harness putting, then wrong screw putting, wrong type of mating. Those failures can happen during integration also. Instead of using a 10 mm screw, if you are using a 12 mm screw, screw will go, but it will be puncturing something inside, either a PCB or a component or a wire. It can create a short or a failure. So this kind of failure has happened in one of the satellite of US satellites. I think it is sport satellite. So when the solar panel got deployed, suddenly power failed and satellite was dysfunctional actually. So when finally they analyzed another satellite in ground, what could go wrong? They found that one screw was having extra length. It punctured the solar panel cable, power cable. So entire power bus got shorted, and it was a catastrophic failure actually. These are called integration time failures. Then environmental failures. Excess temperature, radiation and humidity can create problems. When you are storing the package after testing or during testing also, you have to take extreme care that this environment should not affect the package. Then mission plan errors. Mission plan errors, actually you had designed the package for some mission, but same mission parameter has to be loaded in the mission actually. So one of the problem happened in US and means in Russia, I think. There are two launch stations actually. They are far apart. So the launch vehicle was designed for launching from one station. Okay, let us say Baikonur station. But the parameter loaded in that was for another station. So once it lifts off, it will go haywire actually. So this kind of mission failures can happen. These are called mission related failures, mission plan errors. Then operational failures. Mission is means launch vehicle is deployed, means satellite is deployed, it is in orbit, it is in operation phase now. Now you are giving commands to operate the satellite various ways you want. That time also you can make mistake. Certain commands should not be given at certain times. Okay, then mission can happen actually. Like if there is high voltage system, suddenly if you give high voltage command, suddenly high voltage can come and can create issues. So normally in high voltage what we normally do is we step from low voltage to high voltage, and each step we measure the current to see whether any problem is there or not. So normally 50 volt step we give up to 2500 in Aditya L1 mission, that Papa package. Up to 5000 voltage systems are there actually. So we will be ramping from 0 volt to 5000 voltage in 50 volt step. So this is the mission operation. The proper way you have to give commands. So certain commands cannot be given at certain times, and certain command has to be given in sequence also, like interlocks should be there. So these are the mission related failures. Then human errors. In my personal opinion, most of the failures in space is because of human errors only, not component or material failures. So in ISRO's also I told you, two software errors, it is not a component failure or a material failure, it is a human error actually. So violation of procedures, basic thing is violation of procedures. Then mistakes, human mistakes can happen. Then accidental operations, because some testing is going on, somebody is walking, suddenly if he slips or lose balance, and he can accidentally create some operation actually. Then wrong inputs. Then most common reason for failure is this human errors. And one of the failure in our GSLV mission was there was a system in launch vehicle that if the launch vehicle, all the 4 strap-ons are liquid motors, they will be first firing that, and they will test the thrust. If all the 4 are equal only, they will fire the central engine, which is a solid booster actually. So solid booster, once you fire, you cannot control actually. So this system was there in all the launch vehicles, but never utilized because never had a problem. One of the GSLE, you must have seen in TV actually, when you count down from 10 to 4, these 4 strap-ons will ignite, liquid engines will ignite. When it count to 3, 2, it will test all the pressure of the engines. If all are okay only, it will fire when you count 0 also. So in that case, count 2 came, 1 came, 0 came, central engine was not fired. Booster did not got fire. and all the 4 engines shut off also, because once it is not attaining the pressure, it will shut off. So once you shut off an engine, normally the flame will go upward only. No? Why rocket flame is going downward is because of high pressure only. So when it is standing still without any pressure, if you shut off, the whatever remaining fuel will fire, and it will form a flame around the engine, around the rocket. So we saw in TV that entire rocket is in flame actually. Flame is around the rocket and it is not lifting off also. So this happened because of one of the engine was not generating enough pressure, and this protection system switched off the engines and saved the rocket from mishap. So that engine we removed, and finally we tested what went wrong that. So there are several tubes for taking the fuel into the engine. One of the tube was blocking. Okay, the test done to the tube is that the one ball bearing will be dropped through the tube because in different shapes actually. So it should go through all the shape and come out of the other end. If it is not coming out, means inside dia is not uniform, there is some blockage. So this test has to be done before using that tube for the engine assembly. When they went to the logbook, they found that one of the tube, this test was not done, and the same tube was having a problem. It was blocked. Okay. So luckily we could save that mission because of that protection system. So these are the kind of human errors which will happen during the assembly, integration, testing. So most critical thing is the human error actually. Fingerprint I told you know, for very sensitive circuits, even fingerprint can create a wrong reading actually. Picoampere kind of measurements. And if it is high voltage also, it can arc through the fingerprint actually. It will create a low impedance path. And in space, this fingerprint is oil actually, and this oil will evaporate and create lot of gas actually. So fingerprint. If you use gloves, there is no issue. If you are not using gloves, fingerprint can come, and that in space will degas lot of gas because they are all oil actually. So these are the various areas of failure actually. Failure can happen in various areas. During procurement, you have to be very careful because you will get a wrong device, you may get a wrong package, you may get a wrong speed grade for device, and you may get a wrong temperature grade. So these are the things you should look in the beginning itself. In ISRO, what we do is our main motto is to avoid the failure actually. Okay, we do a lot of failure analysis and root cause analysis, and prevention of failure is the main motto. So how do we prevent failure? We have to start from the beginning actually. Beginning is while procuring the components or the material. So there you have to pay a lot of attention. Then screening whatever components or material you are getting, you have to. No. So screening means whatever components and material you are getting, you have to screen for the specification it was procured for. Then assembly related, tinning, soldering, and already I mentioned. Then testing, already I mentioned, design level test and environment level test, and flight acceptance level test, which I already mentioned. Then sub-assembly integration. Then system level. Once you have a sub-assembly, that sub-assembly will be going to the entire system like launch vehicle. So that time also failures can happen. Then pre-launch and post-launch tests are there. That time also failures can happen. Then launch phase and mission phase also failures can happen. These are the various phase areas where failures can occur. Then impact of failure. Main impact is schedule delay. Okay. Then damage to the system. Some impact means failure may escalate and it can create damage to the subsystems around that. Then it can impact on space systems also. If the failure is happening in space, it can impact other satellites or other space systems. Then it can create space debris, and that debris can be a problem for the other space missions and our own missions also. Then human fatalities, that is also failure can create that much impact. And cost of failure, you have to assess the cost of failure. Okay, depending upon the subsequent failures, you should assess the cost, and the highest cost is when a human failure is there. Then loss of reputation, that is also one failure actually. If many failures are coming to your industry, then your reputation will go. You will not get business actually. So it will lead to loss of business. So these are the impact of failures. So detection of failure. The most important point for prevention of any failure is the how to detect the failure actually. How do you detect the failure? If you are able to detect the failure before it occurs, then you can save the system. So visual inspection is one thing what we normally do. Once we get a package or anything or a component or a material, first we do visual inspection to see whether everything is okay. Because experienced people can see with visual inspection itself whether it is okay or not. Because components also, when we are buying components from various people, the dealers will be different, but manufacturer is same. Okay. So if some dealer is doing mischief, he is bringing somebody's material and just giving same part number and all. But the operator who is regularly doing visual inspection, he can easily find out, no, this is not the original device, it's a fake device. So visual inspection is a major thing to avoid failures. Then continuity and isolation check. Once you make a package, you have a connection where power is there, other interconnections are there. So first you do is that continuity and isolation. Certain pins you know that it will be having continuity with the ground. Certain pin you know that there should be isolation between ground. So these two things we would do. And once you do that, you can ensure that at least when you power it, nothing will happen to that. Then once you power it, you should monitor the power supply current and the surge current and normal current and abnormal current. All these things you should not, and that is one way of knowing any failure. If any current is abnormal, you will know that there is a failure. Or you can even prevent a failure before it happens also. Then test input and outputs. Whatever input you are giving, whatever output you are getting, you should analyze that, then you will know whether there is a failure or not. Then observation of monitoring of parameters. If you monitor the parameters also, you can know that there is some problem. There will be hundreds of parameters you are monitoring. So one parameter may be going out of range. If you are not seeing that, failure can happen actually. So during launch, you must have seen in launch control center, so many people are sitting with so many consoles. So each person is looking into the parameter which is assigned to him actually. He will be only seeing that. So if anything goes beyond that range, he will give an alert. Okay. So like that, all these people are monitoring various parameters and giving alert. Only one person is there who can control this launch vehicle, because during launch vehicle we are not giving any command. Only command given to launch vehicle during launch is the destruct command. Okay, if we feel that a launch vehicle is not going to the intended orbit or intended way, it can create damage to the whatever Earth systems or human, then we will destruct that in space itself. Okay, so that is the command given from ground during launch actually, and that person will be curiously looking into all these things. So he will be looking for hearing the alert given by all these people. If somebody is giving an alert and that alert is very fatal, he has to immediately take a decision. He cannot ask chairman whether I should press this button or not. He has to take a decision to destruct the launch vehicle actually. I think 1 or 2 times only we have done that for GSLV. And observation of monitoring parameters is important, and test data review and analysis. So whatever test data you are getting, you have to thoroughly review that, because certain failure may be hidden in the test data. If you thoroughly review it, you will know that there is a failure hidden in that. It may happen in space. Okay, it may not happen also, but you can find out such hidden failures if you analyze the data. So detection of failure is very important, and these are the ways you can do detection of failures. Then comes the failure analysis. Everything is okay. Failure analysis. So there are several methods for failure analysis. I am listing 1 or 2 only. This is a fault tree analysis or top-down approach actually. So failure has happened. So you are starting from the failure to understand the cause. This is a top-down approach actually. Then failure modes and effect analysis, FMECA we call it. That is actually a bottom-up approach. Once a failure has happened, you are trying to find out the root cause starting from the design itself. So you are looking into the design, what components you have used, what parameters you have considered, what is the derating, what is the power dissipation of the component, what is the voltage withstand capacity, what is the current capacity. You look into all these details of this every component used in that design, then you will find out what is the cause for the failure. That is a FMECA bottom approach. Then Ishikawa or fishbone approach. In this actually this is a diagram based approach, in that causes and effects will be listed. Then from that you will understand what is the cause of the failure, actually root cause analysis. So root cause analysis is very much required for preventing failures in future actually. Once a failure has happened, normal tendency is that we will replace that component or a subsystem, then we will go ahead again with the mission actually. But in ISRO, nobody will be allowed to do that. If I am testing a package, any development activity for a flight, right from the component procurement, everything is monitored actually. If the component procured is not correct, I have to report it immediately. Okay, there is a reporting mechanism, I have to report that. Then when I am testing that component, if any issue is there, that also I have to report. When I am assembling that component in my PCB and that time any issue, assembling time issues, that also I have to report. Then when I am testing, that also I have to report. So every stage of the manufacturing or the package fabrication, we have to report every issue, any abnormality if we are finding, even if it is not leading to any failure, we have to report that, and that will be thoroughly studied to prevent any failure actually. So this is one of the methods. So how to avoid failures? So first and foremost thing is the design review. There will be peer review of design. There will be expert review of a design. So anything we design will be going through several levels of rounds of design reviews. So preliminary design review is there, critical design review is there, various other reviews are there, many review forums are there. So it has to go through all this review process. So most of the errors will be avoided in this review process itself. That is why in ISRO, collective wisdom is there. No individual will be doing anything single-handedly. So there will be a collective activity. So collective wisdom is always there. Then proper selection of devices, materials, and quality, reliability, and compatibility, all these aspects we have to consider. Then we can avoid failures. Then FMECA analysis I already told. We are doing FMECA analysis before the failure also. After the design is over, we are doing this FMECA analysis, then only we are further testing it actually. But after failure also, we will come back and do it once again. Then derating analysis, whatever components we use, we will see whether that component is able to take care of all the extremes of the design. So maximum power, maximum voltage, maximum current, all these things will, and maximum temperature it can withstand, everything will be analyzed, and it is called a derating document. So any violation in derating document, we have to address that. Sometimes we may have to replace that device. Sometimes we will analyze the impact of that this one. If the impact is not very much, and we don't have time to replace that, or we don't have an extra spare to replace that, we may allow that with a little constraint. Then adequate design margins has to be given. Then functional testing is very important. All the functionality has to be tested. Even for software also, all the lines in the software has to be tested. We will not leave any line untested, because in software what happens now, some of the routines will not be tested in normal operations. Only when particular event happens, it will go to that subroutine and act. Okay. But if you want to test a software, we have to test entire code actually. So what we do is we create a situation such that that software goes to that subroutine and execute those lines also. So every line of a software has to be tested. Then environmental testing, then qualification level testing I already told you, for 1.5 times the environment we will test it. Then adequate documentation. So each and every stage documentation has to be there. In space, if you want to use anything, even a nut or a bolt or any material, we should be able to know what is the material this nut is made out of, and who was the manufacturer of that material, and when was it manufactured, and where this nut was made, and which machine it was made. All these details should be available. It's called tracing back to the, because any root cause analysis you should be able to trace back to the roots, so that you will know the failure happened because material was different, or the operator was different, or the machine was different, okay, or even the transportation procedure was different. Sometimes the failure happened due to transportation also. Okay, so these are the things we normally do. Because when you transport this launch vehicle systems from Trivandrum to Shar, it is going by road actually. So Indian roads, you know. So, so when it is going through all these roads, a lot of shock and vibration will come. So finally, we have tested everything perfectly well here. After reaching Shar, we are not thoroughly testing that. We don't have that much subsystem there to test it thoroughly. So we will be doing minimal level testing. So what is the confidence we are having that all this shock and vibration has not created an issue to this package? What we do is we put lots of weighted balls on springs actually. Okay. So each ball will be related to 1G, 2G, 4G, 5G like that. So if any shock is there beyond 1G, that ball will come out of the spring and it will fall down. So finally when the package reaches in shower, we will be looking for these balls which all has fallen down, and they will understand this much shock has come because of this transportation. So there are various methods by which we are preventing such problems. Then safe handling is one thing. Then safe storage also. Everything you have done perfectly well, tested well, package is now ready for integration, but integration is not happening immediately. You have to store it for some time. Okay. So that storing time, you have to keep it very safely. Then failure mitigation. Mitigation help reduce the impact of the failure actually. And monitoring and detecting signs of failure with sensors, indicators and alarms. These are things we use for understanding the failures. Then limited functional operation. If some failure has happened, if you want to mitigate that, you have to limit the functionality, either functionality or certain times, certain situations it may not work properly, but we know that it is not going to encounter that situation, then we can use that. So this is called mitigation actually, because certain failures you don't have time to rectify that failure actually. One of the incident I can tell you, during the Chandrayaan-1 launch, our launch vehicle PSLV C-11 is in the launch pad, and continuously 4 days it was heavily raining. Okay, the launch vehicle is not hermetically sealed, so and we were trying to fuel the rocket. So that time we found that one of the antennas giving a wrong signal, saying that destruct command is given. Okay, so with that we cannot fly it now. So finally they understood that that package has failed, but package is inside the launch vehicle, and normal procedure to replace that package is that you have to destack the entire thing. First you have to remove the satellite heat shield, then that stage, then you have to take out this package. Then if you want to reassemble with another new package, again you have to stacking all these things. So in launch pad you cannot do that. You have to bring this entire thing to the assembly building and redo it. But there is no time actually. So that time Madhav Nair was chairman. He told we cannot shift this Chandrayaan-1 launch, because if you shift the launch window, it may appear in next month, sometimes next year, sometimes it may not happen also. So you don't want to shift the launch time or launch date. Then what is they told as per procedure we need 4 or 5 days to do all these operations. So what I understand is that he told them, you are given free hand, you do whatever you want to do, okay, but we cannot change the launch time. So what they finally did is they removed the antenna. There is a cutout, through that only this antenna is connected to the package. So they removed the cutout from the launch vehicle. It is fully loaded with fuel and everything. Nobody is supposed to go near that, but we have to do that. So they removed the cutout, and with their hand they removed the cable. Then another package was brought from Trivandrum to Char. By the time, then they screwed that package outside the body actually, because inside they cannot keep. That cutout cannot take the package inside. So they screwed outside, they connected the cable externally. It is still raining. Okay, so they had to protect the package. None of the packages are hermetically sealed. So they did protection from rain also. With that only, our Chandrayaan-1 mission was successful, PSLV C-11. There are several failures during the launch pad itself. There was a fuel leakage. So many other things were there. I am not telling that because a lot of time will be required to mention all those things. Okay, so monitoring, detection, all those things are important. Then limited operation conditions. Okay, so these are the mitigation thing we are doing. Then reliability. So coming to reliability, any component or package, if there is a problem, initial hours itself it will fail actually. So first initial hours, if you see, the failure rate will be very high. This is called a bathtub curve actually. Initial days or hours it will be high, then it will stabilize. Okay, that is the time we are going to operate or use that package. Then the fag end of the life, again failures will increase. Okay, so you should use the package during that flat portion. So this is one thing we have to do for high reliability. Then component material quality we have to ensure. Then screening of components, burn-in etc., because we have to do burn-in of components, 168-hour burning and all we do. Then life cycle documentation and reviews I already mentioned. Then production process and standards we have to follow. We have to follow all the standards of production norms. Then test and evaluation as per norms we have to do. Then a test and evaluation depending upon various missions it will be different. Then proper handling and storage. So reliability by design is one method we can get high reliability. Then reliability by reviews also we can get. Reliability by using quality components and materials we can get. Then by different standards, following different standards we can get reliability. Then we can get fabrication process we can achieve reliability. Then by testing also we can achieve reliability. By putting redundant systems also we can get reliability. Thank you so much. I will stop here because other slides are already you know what missions of Chandrayaan-1 Mars mission is and all. If you have any questions, I can answer. Regarding mission also you can ask. I will be happy to answer that. How much time I took?
Sorry, how this obsolescence is managed in ISRO? Because that is one issue that we are
Yes.
also facing.
Yes, yes.
Uh,
It's a major issue actually. One thing is that most of the major manufacturers they give advance warning that they are taking out this product within 5-year time or 10-year time. So that warning we will take and we will circulate to each and everyone. Every designer this information will be passed around so that when he is going to use that component he should be very careful. That is one thing. Second thing is that we know that any time any manufacturer can make it obsolete. So if we are going to use that, we will buy bulk considering our future requirements and keep it with us. Earlier there was a time ISRO that whenever we use some FPGA or processor, the moment NASA or American government comes to know that we are using that, they will force the manufacturer to stop that device actually. Okay. So this has been happening in the past. So we surveyed by buying bulk. Okay. So this is one method we are doing, buying bulk. Yes, it is possible. I am one such person. I have used the commercial grade components for the Mars mission, Chandrayaan-1 mission, Chandrayaan-2 mission, and Chandrayaan-3 mission also. In Mars mission, the Menga payload has worked 9 years in orbit, even though it was meant for 1.5 years. 9 years it has worked, and it has surveyed in Earth orbit also 1 month, crossing Van Allen belt. And none of the components had any problem. It was pakka commercial grade components, 0 to 70 degree.
There is a failure
Ah,
stuck at 1 or stuck at 0 in one of the components,
yes.
commercial components, then there stands for failure, isn't it? So
Yes.
how did you take care of that when
Actually,
you
these stuck at 0 or 1 latch up errors can happen even with mil grade and space grade components also, because none of these components are protected from high energy radiation or high energy protons or neutrons. Only normal level of radiation there is a protection actually. So when that happens, these space qualified components also will fail. But commercial grade components may fail, chances are more compared to mil and space grade. But what we are doing is commercial grade components are used for non-critical areas, like scientific experiment is a non-critical area. And another thing is you can have redundant systems. Okay, cost is less. So normally if I say resistor what we use normally 1 rupee for resistor, the same resistor if you want to buy a space grade or mil grade, it is 2000 rupees. That much difference is there. Okay. So 100 to 2000 times price difference is there. So instead of making one space qualified system with one resistor, I can make 3 systems with 3 resistors. Still cost will be much less. So I will have redundant system so that I can take care with less cost. So that is another method. Then ruggedization is another method. You use a normal commercial grade components, you ruggedize it so that it will not get affected by radiation or other things, by temperature or thing. One more method is that you upscale it. Means you do whatever screening test you are doing for the million space grade, same test you do this for this also. If it surveys, you will get the confidence that this is also okay. So that is one method we are doing. We will upscreen it and see that it is okay. Then once we get the confidence, we will use that. So now in ISRO's missions, we are using industrial grade components also, launch vehicles. Failure mode effect analysis actually. So that is an analysis we start from the design itself. Whatever the value of the component, type of component, package, every aspect of that design will be taken care during the analysis actually. And whether any failure happen in one system, whether it can escalate to another system. Okay, because you must have noticed the failure in one system, but the cause may be sitting in another system actually. So this is the escalation actually. So failure is escalated from the other system, but failure happened in this system actually. So if you start analyzing only this system, you will never be able to find the fault actually. So FMECA will take care of all these things, failure escalation also. Any other questions?
Sir, when you're taking care of the redundancy, is there any standard procedure or normally based on the experience you will provide the redundancy?
We give redundancy that 2-3 types we are using. One is dual redundancy, triple redundancy, and quad also. And for Gaganyaan missions, we are going for quad redundancy. But redundancy we will be giving for critical components or critical subsystems like power supply. We have to have redundancy because very critical actually. Power fail means the entire system will fail. So normally power supplies will have this one, but motors you cannot have redundancy because motor is going to actuate the physical piston, no? So you cannot have more motor to actuate that. So motor will be having only one actually, but motor still you can have multiple coils, multiple drive systems you can have. Okay, so certain things you cannot have redundancy, it is not possible, but certain systems you can have redundancy wherever it is possible, wherever it is required based on our experience and logical thinking we will introduce. Not all systems will be having redundant systems.
Sir, I would like to tell one more point.
Yeah.
During our initial discussion, we were telling we were having association with the ISRO 20 years back.
Yes.
But that is not right because we are having association with ISRO long back, even before that.
Okay.
When I joined in 1995, 96, 98, during that time we had a project with ISRO for the onboard computer, FPGA design using for onboard computer. And then we also had some test vector design for some of the avionics packages that was in the avionics division. Even for the under Ignatius sir also we had some projects.
Yes,
So
yes, yes.
our association was right from
Long
then
back,
it's long
decades.
back. Yeah, yeah.
I said actually my association.
Yeah.
That was only
No, not
20
about
years.
you. Even we in
Ah,
CDAC
okay,
also
okay.
we were saying 20
Okay,
years
okay,
back.
okay.
So just
Yeah,
for
I
the
know,
information for our youngsters.
Yes, yes. I know that you are doing actually same level of expertise is here also. And one more point I want to mention is that even though ISRO is doing very high class research and high class results is coming out of that, we are not excellent people in ISRO actually. People are not excellent people actually. People are just ordinary people like you and me only. Okay, but we are able to do excellent research or outcome is only because of innovation actually. We are striving for that innovation. That is why we are able to achieve this. It is not because of any excellent people are there or super brains are there. It's not because of that. Everyone is contributing their level best, and everyone time wise they are contributing 100 to 200 times also. That is why we are able to do this. So innovation is the key actually. I can tell you almost 100 missions to the moon has happened before we found water on moon actually. Almost 60 years Russia, America, and Japan, other people have gone to moon to find water. They could not find water actually. Astronauts like Neil Armstrong and other people also have gone to moon. They walked on the surface. They conducted experiment on the surface. They brought back rock samples from lunar surface to Earth and analyzed whether any trapped water is there or not. They could not find water. Then they declared that moon is bone dry. But we were able to find water on moon just by sending an instrument from ground, and the total cost of the development was one package is almost 50 lakhs only. Okay, with that 50 lakhs we were able to find water on moon is only because of innovation only. It's not because of any super brain or anything. So innovative thinking is the key for achieving excellence actually. Any other question?
I mentioned about 20 years experience of our group, strategic electronics group, basically.
Okay.
Also to mention, there are around 60 people have joined online. So any of the members who joined online can also ask questions now. We will allow a few questions from online joiners.
Hello.
They can
Hello. Hello.
Yeah, you are audible. Continue.
Yeah, sir. I am Atul from CDAC Hyderabad.
Yes,
Sir,
please go ahead.
yes, sir. I want to ask about cyber security related issue in the scenario of Chandrayaan 3. Sir, is any role in Chandrayaan 3 mission of cyber security?
Are you talking that is there any issue with the cyber security for the mission?
Yes, sir.
Okay, cyber security is always there actually. But
How?
ISRO, we are having our internal network system, so that is not connected to the internet or external world. So we'll be mostly
Oh,
using that for the all the launch vehicle operations. But certain times we have to use internet also, like the Chandrayaan 3 mission. We were actually using the radar data of the America and their JPL lab. Okay. So
hmm.
JPL lab, they are putting their data in a cloud, that is I think Amazon cloud. Okay. So we wanted to use their data, live data during the mission, but it is available only in Amazon cloud. But ISRO don't want to connect our system to the internet or Amazon cloud.
Oh,
So there will be a lot of clash of interest. We tried
uh,
to tell them that you should give otherwise directly to you using hot link to us, but they did not bother. They said this is the only way we can provide. If you want, you use it. Finally, we are the user, so we have to agree to them. Finally, we have to connect our ISRO system to their network. So that is the time vulnerability is there that if any cyber attack is coming, it can create problem. But normally, we are protected from the cyber attack.
fine, sir. Thank you. Thank you so much.
Okay, thank you.
Anybody else from online joiners would like to ask questions? Any of our product engineering team would like to ask questions? Okay. Would you? Okay, sir. Then we'll.
Okay, okay. Thank you. Thank you so much.
Very nice session, sir.
Thank you, sir. Before we conclude, I would like to take this opportunity to thank the chairperson and all members of the National Space Day Celebration Committee at CDAC Thiruvananthapuram for their active involvement in organizing this function in such a short span of time. I invite Sri Prem Krishnan N, Scientist E, Strategic Electronics Group to propose the vote of thanks.
Good afternoon to all of you. Shri Pradeep Kumar P, Deputy Head ACD Digital Systems Group Avionics Entity VSSC. Shri Rajesh KR, Scientist G and Group Head Strategic Electronics Group CDACTVPM. Heads of groups, sections, divisions, and dear colleagues and friends. It's a privilege for me to have to to have been given this opportunity to propose a vote of thanks on this occasion. So when we started planning the event, we thought we should have a talk on a topic that is often, not discussed widely, even though it is so critical to our work, which is about, failure analysis as part of space missions, and this was suggested by Sri Rajesh KR. So I was also a bit skeptical about, first of all, we had to find a speaker from ISRO, and we were also skeptical as to whether they would agree to give a talk on this. But then, the thought process was that success of space missions are built on the lessons learned from various failures. It was the same with, the Soviet Union, because, before Yuri Gagarin flew into space, there are multiple missions that failed. The same was the case with the Apollo mission also, with the moon. And it's the same with us also. We also encountered multiple failures. So despite limited time, Sri Pradeep Kumar accepted our invitation, and then he agreed to, cover the topic. And I also would like to apologize for having, probably you lost your sleep yesterday. Anyway, thanks for, yeah, it's part of life. But then, thank you for putting in that kind of effort, for this talk, sir. So thank you, sir, from the bottom of my heart, for taking the road that is not often taken, and especially giving a talk on this failure analysis at such a short notice. So on behalf of the entire CDAC fraternity, I wish to place on record our heartfelt thanks to Sri Pradeep Kumar for consenting to our request to be an invited speaker, and for enlightening us with this rich experience. It was on full display. Your hands-on experience at ISRO for 35 years was on full display. We could gauge the depth of your experience. So thanks for being part of this event, sir, and it was a great learning experience for all of us to listen to your talk. Thank you. We wish to I wish to express my sincere thanks to Dr. Kalay Selvan, Director CDACTVPM, for extending all support for the first National Space Day celebrations. I also wish to thank Sri Rajesh KR, Scientist G and Group Head, Strategic Electronics Group, for his constant guidance and encouragement, which helped us organize this event as a very short notice, and also for giving an overview of the CDAC's involvement in the space sector. Before I conclude, I wish to express sincere gratitude to all my colleagues at CDAC who helped us in many ways to organize this year's celebrations. But for your unceasing support, we would not have been able to organize this event within a very short span of time. I once again thank all of you for being part of the first National Space Day celebrations, and a special thanks to all of you, nearly 60 of you. That's a number much higher than we had expected. So I also wish to thank all my colleagues who have joined online for this event. Thank you all once again.
Also, one more word to add. Sir agreed to share some of the slides, which will be very useful for especially our hardware and software engineers. So once that we get slides, we will share that. Thank you very much, sir, for the kind.
One more offer from my side. Any doubt you can ask me. I will be happy to help.
Actually, we are planning a session whenever that time permits, sir, for all our engineers, so that regarding this activities, how the design phase, how the testing phase happens, and the failure analysis and all. So we will plan and we will discuss, sir. So that will be a great learning phase for our young engineers as well. Thank you very much, sir.
I shared my phone number and email ID also. You want me to contact? Phone always I am available. Normally sleeping around 12 to 1 a.m. In that time I am available.
Thank you, sir. Thank you very much.
Thank you, sir. Remembering the words of Stephen Hawking as we move towards the end of this function, the universe is under no obligation to make sense to us. Yet, through innovation, we can unravel its mysteries. Thank you all for your participation in today's function. Let us conclude with the national anthem, paying tribute to our great nation that continues to reach for the stars. National anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत